Hi, everyone. Thanks for joining this pre-recorded talk. My name is Gerhard Fernandez Barranco. I'm a postdoc at the Albert Einstein Institute in Hannover. And today I'm going to talk to you about a transistor-based transimpedance amplifier for the LISA QPRs. There is a long list of people that have contributed, are contributing to the development of the LISA QPRs. And that you can see here in this list. We, specifically at the AAI Hannover, are focusing on the development of a discrete solution for the transimpedance amplifier of the QPRs, also known as the front-end electronics. But what's the front-end electronics and why are they so important? Well, first, let me give you a short overview of the photoreceivers in LISA. So on the left hand of this slide, you can see an early version of the LISA optical bench, and what you see highlighted are the 12 QPRs on an optical bench. So the QPRs are the devices in charge of the optoelectrical conversion in the LISA instrument. So they get the optical signal in watts and convert it into an output voltage. But this is done in two steps. First, a photodiode converts the optical power into a photocurrent. And then this photocurrent is converted into an output voltage in a transimpedance amplifier, a set of electronics called the transimpedance amplifier. And the combination of these two, the photodiode and the transimpedance amplifier, is what we call a photoreceiver. In the particular case of LISA, the very low optical powers that we aim to detect make the noise of the transimpedance amplifier critical. That's why we need to pay special attention to this transimpedance amplifier, to these front-end electronics, and try to reduce its noise as much as possible. But we can't forget about the bandwidth and the power consumption of the transimpedance amplifier. We also need to have enough bandwidth in megahertz range due to the heterodyne frequencies of the LISA instrument. And also we should keep the power consumption as low as possible, since the QPRs are on the optical bench, which is a very sensitive area to thermal fluctuations. And there are many of them. There are 12 QPRs in an optical bench, so the power consumption is important. The classic solution for the transimpedance amplifier is just to attach an operational amplifier with a feedback resistor to the photodiode, which is represented here by a current source and a capacitance. And there are basically two ways to reduce the noise of the whole QPR. One is to reduce this junction capacitance of the QPD. And this is what some colleagues from the QPR working group are doing. If you're interested in this topic, please see the poster by Niels van Bakkel. And the other option is to choose an operational amplifier with the lowest noise possible. But since the selection of these amplifiers is limited, we started investigating a solution based on bipolar transistors, of using heterojunction bipolar transistors as the first stage, because these transistors show a lower noise compared to both op-amps. And that's what you see on the right-hand side of the screen. We developed this transimpedance amplifier with an initial cascode stage with two transistors, the BFP 740, which has a space-qualified counterpart. And then there is a second stage based on an operational amplifier, the AD8038. And then the loop is closed with a feedback resistor, which sets the value of the transimpedance gain, which in this case is 42.2 kilo ohms. The operating point of this transimpedance amplifier is set by a combination of the voltage here, essentially the voltage at the inverting input of the operational amplifier, and the value of this resistor, which sets also the collector current going through the transistors. We created many prototypes, many QPR prototypes based on this topology, and they were successfully tested, showing a lower noise and a lower power consumption than their op-amp only counterparts. But here you can more clearly see these results and the evolution. The green line here shows the input preferred current noise, so the noise of the QPR for the transistor-based topology that I showed in the previous slide. And you can see how the noise is lower than in the op-amp case, the purple line, for the whole LISA frequency range, so from 5 megahertz up to 25 megahertz. Additionally, the bandwidth is sufficient for LISA. It was measured to be 37 megahertz, and the power consumption was 56.2 milliwatts, lower than the 200 milliwatts requirement for the LISA QPRs. Our colleagues from JAXA in Japan took this transistor-based topology and gave it a little spin, improved it further by doing several modifications. For example, removing one of the two transistors of the cascode because they realized that the performance wasn't limited by this, so one transistor could be enough. They also reduced the supply voltage to decrease further the power consumption. They also reduced the transimpedance amplifier gain, lowering this resistor here to avoid potential saturation of the QPRs. And finally, they also created a prototype using space-grade transistors. And in this slide, you can see the input refer current noise that they measure in all 4 channels of this prototype, the one that I showed you in the last slide. You can see that the noise stays below 2 picoamps per square root of hertz, which is the LISA goal, up to 25 megahertz, the highest heterodyne frequency in LISA. And that's true even for a 0.4 picofarad input capacitance, which corresponds to a 1.5 millimeter diameter QPD. So those were also very good results. Apart from that, the bandwidth was also measured, and it's 30 megahertz, which should be sufficient for LISA, and the power consumption was 49 milliwatts, which is also well below the 200 milliwatts requirement for the LISA QPRs. After the performance of the transistor-based design was verified, the efforts have focused now on creating a prototype that can show TRL6. And this is what I show you here. So this last iteration of the design features, for example, a secondary PCB connected via a flex section to the main PCB so that the QPD can be adjusted with high enough precision. The layout was also adapted to fit the housing being developed for the QPR. If you want to check more details on that, please see the poster by Robin Cornelisse. So the performance was tested also in this last iteration, and we could verify that this new layout and the extra flex section didn't affect the performance. So the noise and bandwidth specs were still met. But we did an additional test, and that was a test for EM compatibility. And that test partially failed, and we saw a strong coupling at the output of the QPR from electromagnetic interference. And if you want to know more about this, please check the talk by Ed de Vries. So what we are trying to do now for TRL6 demonstration is to solve 2 issues. First, add some measures for EMC, for example, using better connectors and adding filtering and regulation of the power supply lines, and also replace the only op-amp in the transistor-based design, which is this low power 88038, which has some space heritage. It was using 2 space missions. That's why it was chosen, but it's not space grade. So we want to replace it by space grade op-amps, and there are 2 candidates. One is the LM6172, and the other one is the AD8001. So to sum up, we have investigated a discrete solution for the transimpedance amplifier of the LISA QPR, also known as front-end electronics. This solution was based on bipolar transistors in combination with an operational amplifier, and this solution meets the requirements for noise, bandwidth, and power consumption. Several prototypes tested independently at different institutions verified such results, which makes the discrete transimpedance amplifier front-end electronics a valid fallback solution for the LISA QPRs, since the ASIC solution is still the baseline. And to achieve TRL6, some modifications are required, for example, making the design EMC compliant, and also replacing the op-amp with a space qualified one. And with this, I want to thank you for your attention.